In this video, I'm going to go through A-level OCR A-level chemistry, specification A. This is paper 1. It's the June 2018 paper, and I'm doing the second half of this paper. I covered the first half in an earlier video. Starting off question 19 then. Right. This question is about acids and bases. So there's ethanoic acid. A student is going to carry out its experiment to find the pKa of the acid. Okay, so write an expression for Ka first of all. Well, before I write that, I'm going to just write down this bit because I need the next part of the question. Ha dissociates from A minus and H plus. So we want the expression for Ka for ethanoic acid. So we want the concentration of hydrogen ions, concentration of the conjugate acid, divided by the concentration of the conjugate base, divided by the concentration of the conjugate acid. Right. Calculate the next question is then to calculate the pKa of ethanoic acid. Okay, so we're going to do that now. Right. So how are we going to do that? Well, they give us the hydrogen ion concentration. They give us pH, which is 2.41. So we know that H plus concentration is going to be equal to 10 to the power of the pH, which is 2.41, which is equal to 3.89 times 10 to the minus 3 moles per decimeter cubed. Now, in this weak acid, you can see that for every H plus that is made, you make an A minus. So we know there that H plus is equal to A minus. So we also know that A minus is going to be equal to 3.89 times 10 to the minus 32. We also know the concentration of HA because they tell us that the concentration of it is 0.87 mole per decimeter cubed. Now, the real concentration is going to be of HA is going to be a tiny bit lower than that because some of it, of course, dissociates to form A minus and H plus, but because it's a weak acid, it's only a tiny amount, so we can kind of ignore that. It's an acceptable approximation. So now we've just got to put our numbers into this equation here to work out Ka, and then we can work out pKa from that. So putting the numbers into that, we get Ka is equal to 3.89 times 10 to the minus 3, and the concentration of the conjugate base is the same as that, so that's going to be squared over 0.870. That works out to be 1.74 times 10 to the minus 5. That's Ka. The question is asking us for pKa, so we take a minus log of that. So pKa is equal to the minus log of the Ka. Minus log of this number is equal to 4.76. They say to give it to 2 decimal places, so there's our answer, 4.76. Okay, sodium carbonate is a base using washing soda. Contains the carbonate ion shown below. Draw the dot cross diagram for that. Okay. So what we're going to have there is, here's our carbon double bonded to that oxygen, single bonded to these. Okay, so the double bond, we'll do the carbon's electrons as dots, and we'll do the oxygen electrons as crosses. So we've got a double bond, so we've got a dot and a cross and a dot and a cross there. Now, oxygen is in group 6. I've only drawn 2 crosses for that oxygen, so I need to draw 4 more. Got 6 inside the shell, so it's got 2 lone pairs. Right, now this oxygen has got a single bond, so a dot and a cross. And this one's single bonded, a dot and a cross. Let's think about the carbon. Well, we have done 4 dots for the carbon, and it's in group 4. So there's no more electrons to draw for the carbon. There's no lone pairs. They're all involved in bonding. So let's just finish off the oxygens. Right, for this oxygen, I've drawn 1 dot. Sorry, 1 cross. So there are 5 more electrons. So I'm going to draw 1, 2, 3, 4, and 5. But this has got a negative charge on it. So it's got an extra electron, which is taken from somewhere else. Do that in green. And the same on this this oxygen is exactly the same. Okay, so all of them have got 8 in their outer shell. That's and there's a 2 minus charge on that because you've got those 2 extra green electrons. Okay, question about halogen group of elements and some of their compounds. All right, the boiling point of the halogens is shown below. The boiling point increases. Right, so we've got why have we got an increase in boiling point? Well, all of these molecules are diatomic. Obviously, we're not going to have a permanent dipole because it's the same atom. So we're talking the intermolecular forces present are London forces. And the London forces get stronger as you go down the group. Why do they get stronger? Because the number of electrons increases as the atoms get bigger. So you've got more electrons, so you've got more points of contact. So you've got stronger London forces, higher boiling point. Okay, right. Hydrogen iodide is decomposed into its elements. The decomposition is much faster in the presence of a platinum catalyst. Complete the energy profile diagram for this reaction using formula for the reactants and products. And we've got a label: activation energy with no catalyst, activation energy with a catalyst, and delta H for the reaction. Okay, so first of all, it's an endothermic reaction. So here are the reactants, and here are the products. The products have slightly more energy because it's endothermic. Right, so the reaction profile is going to go like that. Okay, what is delta H for the reaction? We're going to label that's delta H there. The activation energy for the reaction without a catalyst is going to be this bit here. Call that EA. And with a catalyst, it lowers the activation energy. So I'm going to draw that slightly lower. And the EA with the activation energy with the catalyst EC, I'll draw there. A little bit messy, that diagram. Okay, so that's a fairly straightforward, almost a GCSE question, really. Okay, and that is going to be 9.5 kilojoules, isn't it? Right. Okay, compound A is an oxide of chlorine that is a liquid at room temperature and pressure. Okay, so it's an ideal gas equation. So we've got to find out the molecular formula of compound A. 4 marks for this. Well, so there's 2 equations you've got to use. One, of course, is the ideal gas equation. PV is equal to nRT. N is the number of moles. So we're going to rearrange that to get N, which is PV over RT. And then we have to relate the number of moles to the MR and the mass. So moles is equal to mass over MR. So rearrange to get moles is N. Okay, so rearrange that, we got MR is equal to mass over moles. Call that N. So we're going to work out N first of all. That's the first thing we're going to do. And then we're going to, number two, we're going to put the value of N into that equation to find out the MR. So let's do find out the number of moles. Right, so we've got to be really careful with the units for the ideal gas equation. Right, so they've nicely given us the pressure in pascals, not kilopascals. So there's no conversion there. So it's 1 times 10 to the 5 multiplied by the volume. Now the volume is 76 centimeters cubed. To turn that, we've got to turn that into units of meters cubed for the ideal gas equation, which everyone always forgets. So we divide that by a million. Okay, so that's going to be 76 over 10 to the 6, or a million centimeters cubed in a meter cubed. Or the ideal gas constant 8.314, and T, right, that's the absolute temperature in Kelvin, so 100 degrees C, add 273, that's a 373. Put the numbers into the calculator there, and we get 2.45 times 10 to the minus 3 moles. Now we've got to put that number into this equation, okay, to work out the MR. So the MR is equal to the mass of the stuff, which they had 0.4485 grams, divided by the number of moles. That works out to be 182.9 gram per mole. That is the MR of the compound. Right, now we've got to use so we've got to use that to work out the molecular formula of the compound A. Right, so now you probably know that the oxidation states, common oxidation states of chlorine are +1, +5, and +7. Right, let's try so if it's got a +5 oxidation state, the formula of the oxide is Cl2O5. So that would be, what would be the MR of that? It would be 35.5 times 2 for the chlorines, plus 3 times 16 for the 5 times 16 for the oxygens. 151, so that's too low. So it's probably the +7 oxidation state, and the formula of that oxide is going to be Cl2O7. And if we work that out, yeah, that is equal to 182. So that is the molecular formula. Just check that, it's 182 or 183, so it's 71 plus 7 times 16. It's actually 183, which is pretty close to what the answer we got here. Okay, so the molecular formula of the compound is Cl2O7. So a bit of calculation, and also you need to know a little bit about the chemistry of chlorine to come up with the answer there. Okay, so now we have got a big titration question here. Right. Okay, so we've got a group 1 metal, and it's iodate. So group 1 metals are always M +1 ion. So the formula is going to be MiO3. We've got to try and find out basically what the identity of M is in this equation. That's what we're going for. Okay, so they dissolve the iodate in water, step 1, make it up to 250. Okay, so let's draw a little picture there. So we've got our 1.55 grams in there. And we're going to take 25 of that out. so 1/10 of it, and put it into a conical flask. And the conical flask is going to contain acidified potassium iodide. What's going to happen there is we're going to make some iodine in there. So that will react to form iodine. And then we're going to titrate that against sodium thiosulfate. Okay, it tells us here in step 3. So here's our burette. There's our sodium thiosulfate in there. Thiosulfate. And that's concentration 0.15 mole per decimeter cubed. And the titer, well, let's have a look at that, what the average titer is. So, right, so it keeps repeating step 1 and step 2 and step 2 until he gets concordant titers. Right, so they give you the table there, so I've just subtracted it to work out the titers. And you can see concordant titers have got to be within 0.1 of each other. So the only 2 concordant titers are these 2, runs 2 and 3. And if you take an average of those, obviously it's going to be 23.80 centimeters cubed. That's our average titer. And I'll put that in there, 23.8 centimeters cubed. Right. Now, a bit about uncertainty and so on. The uncertainty in each burette reading is 0.05. Calculate the percentage uncertainty in the titer. Right, now you take 2 burette readings, so you've got to double that. So the percentage uncertainty is going to be 2 times that, which is 0.1, over the titer, which is 23.8, multiplied by 100. So that gives us 0.42%. Okay, to 2 decimal places, there's our answer there. Now, how should this student determine the endpoint of this titration accurately? Okay, well, what we have got in the flask is we have got iodine, which is a sort of orangey color. As you run in the thiosulfate, that's going to get paler. The orangey color is going to get paler and paler and paler. Just before it disappears, to visualize it better, what we do is we add starch. So you're going to say add starch when you're getting pretty close to the endpoint, when the color's gone very pale, and it will go blue-black. The starch forms a blue-black complex with I2, and then you can continue adding the thiosulfate until the blue-black color completely disappears. So you need to add starch to do this accurately, really. That's the key point. So one mark for the starch, 1 mark for the disappearance of the blue-black color. Now we've got to determine the relative formula mass and the formula of the group 1 iodate. Okay, so what I'm going to do is I'm going to just paste down that picture that we did up here with a bit of working out in it already. Okay, and what I've done is I've also pasted the instructions there again, so I can see them. Okay, so there is a little. Right, so what we're going to do first of all is we are going to find out the moles of thiosulfate, okay, because we know the volume and we know the concentration. So I'm going to write down moles of thio. Moles of thiosulfate, conc times volume, 0.15 multiplied by the titer, 23.8 over 1,000. That gives us 3.57 times 10 to the minus 3 moles of thiosulfate. Right, so now look at the equation there. 2 moles of thiosulfate react with 1 mole of iodine. So the next step is say, how many moles of iodine do we have in the conical flask there? We've got to halve it. Okay, so moles I2, 3.57 times 10 to the minus 3 divided by 2. That is equal to 1.785 times 10 to the minus 3 moles of iodine. Right, now if we look at this equation here, 1 mole of iodate gives us 3 moles of iodine. So to find out the moles of iodate, and that will be in 25, don't forget here, moles of iodate in 25 is equal to this number divided by 3. Which is equal to 5.94 times 10 to the minus 4. Right, that's in 25, but we need to find out how many moles in 250, because that's all of it. So we multiplied that by 10. So that's 5.94 times 10 to the minus 3. Okay, now we're at the point where we know the moles of iodate, and we know the mass of iodate, which is 1.55 grams up there. So we know the mass and the moles, we can work out the MR like we did in the last question. So MR is equal to mass divided by the moles. It's equal to 1.55 divided by 5.94 times 10 to the minus 3. That works out to be 260. Okay, now we've got to find out the identity of the metal in this. So we know the formula, because it's group 1, the formula is going to be that, because this is a 1 plus I and the iodate is 1 minus, of course. Right, so we know that the MR of the whole thing, is 260. And now, how much is the iodate bit of that way? So it's going to be 3 times 16 for the oxygen, that's 48, plus the iodine is 127. So that bit weighs 176. So we've got to subtract that from the 260. That gives us is equal to 84. Okay, so if you look in your periodic table, rubidium in group 1 has got a relative atomic mass of 84.1, which is pretty close to that. So we can determine that the iodate is rubidium iodate, which is RbIO3. That's the formula of the compound. That's what we set out to find out. That's done. Right, next question. Okay, so some electrode potentials there we're going to need. Right, electronic configuration of the nickel atom. Okay, so here's nickel. I've just pasted a bit of the periodic table. Right, so it's going to be 1s2, 2s2, 2p6, 3p6, sorry, 3s2, 3p6, sorry. And then we get to that's argon. We get to potassium, that's 4s1, calcium 4s2. And then we're going to have the d orbital, so d1, 2, 3, 4, 5, 6, 7, 8. So nickel is 3d8. We should put the d first and 4s2. Right, so when nickel forms the Ni2 plus ion, the electrons are lost from the 4s orbital. So it is that's going to be 2s2, 2p6, 3s2, 3p6, 3d8. Right. A standard cell is set up in the laboratory with the reaction shown below. Draw a labeled diagram to show how this cell could be set up to measure its standard electrode potential. Okay, so include details of solutions and the standard conditions required. Okay, so what we're going to have there is right. So we want a beaker of nickel. Nickel sulfate probably, basically 1, and it's going to be 1 mole per decimeter cubed. Any nickel salt will do. And then we're going to have a strip of nickel metal in there, the element. Okay, because we've got that there. And then on the other electrode, we're going to have iodine, 1 mole per decimeter cubed, and iodide ions, both 1 mole per decimeter cubed. This will probably come as potassium iodide, yeah, in there. Now we are going to need a platinum electrode there because we haven't got any metal, so this is going to be a piece of platinum. And we are going to need a salt bridge here. That's usually filter paper in saturated potassium nitrate. Filter paper soaked in potassium nitrate solution. And we need to have a voltmeter here. It should mention that it's high resistance voltmeter to stop any current flowing, otherwise the voltage is going to change. Standard conditions, we should carry this out, all concentrations of 1 mole per decimeter cubed, as we said earlier, and also we should make sure it's 298 Kelvin standard temperature. Right, 4 marks for that. That's everything there, I think. Right, now right, so we've got to predict the standard potential of the cell we've just set up. But this is the reaction, just to paste it down there again. Right, so the 2 half equations we're going to need there, we are going to need this one, and we're going to need that one. Standard potential of the cell, well, E cell is equal to E right, which should be the most positive one, and the most positive one in this case is the iodine, minus E left, the nickel. Right, the value for the iodine is 0.54, and the nickel standard potential is minus 0.25, so that's going to give us 0.79 plus 0.79 volts. Okay, right, we've got to use the information in table 20. What will happen, the overall equation for the oxidation of Fe2 plus by acidified hydrogen peroxide. Okay, so let's look at the 2 half equations we want there. It tells us the direction of the reaction. We don't need to work that out. So we've got Fe2 plus, and we've got hydrogen peroxide, just to check that that one would go forward because it's the most positive, and this one would go backwards because it's the most negative. Right, now this is a 2 electron process, and this one is only 1, so we have got to multiply the ion 1 by 2. So we're going to have the equation is going to be H2O2, I'm going to leave out the state symbols, plus 2H plus, plus we've got to double that one, so it's 2Fe2 plus, and that's going to go to 2H2O and 2Fe3 plus. Okay, zinc reacts with acidified dichromate, okay, to form chromium ions in 2 stages. Explain why this happens in terms of electrode potentials and equilibria, and include overall ionic equations for the reactions which occur. Right, I think I'm going to copy that table again. And paste it down here, 1 minute. Okay, so right, which half equations are we going to be interested in? Right, we need the dichromate one here, and we need the zinc one, and later on we're also going to need this one here. Okay, let's look at the 2 ones I've marked in red first of all. So first of all, which one is the most positive? Well, it's the dichromate one. So this one is going to be best at, it's positive, it's best at taking in electrons. It's going to take in those electrons and go forwards. This is the most negative one. It's best at giving out electrons. So it's going to push away those electrons, it's going to go backwards. Right, we need to so combine those 2 half equations, but we need to multiply this one by 3 because that's only 2 electrons and the dichromate is 6 electrons. So the first reaction that's going to occur is dichromate plus 14H plus 3 zinc is going to go to 2 chromium 3 plus, 7 waters, and 3 Zn2 plus ions. Okay, that's the first equation. Now, what's going to happen next is that the zinc can then reduce the. So I'm going to color these. I'm going to rub these out. We need to. So the zinc can then react with the Cr3 plus that's been made. So we're going to need to look at these 2 half equations. Do them in yellow. Right. Now, which one is the most positive? Well, it's this one. So this is going to be the best at taking in electrons. So that's going to go to Cr2 plus, and this is the most negative, so that's going to go backwards. Okay, so that's what's going to happen. Now we need to balance those equations because this is only 1 electron, so we need to multiply the chromium one, whereas this one is 2. We need to multiply the chromium one by 2, so it's going to be 2 Cr3 plus a zinc goes to a Zn2 plus and 2 Cr2 plus. That is that question done. Right. Now, this is the last question in the paper. Okay. Right, let's look at reaction 1. 3 different reactions of copper. So identify C to F by formula, and you've got to include equations and talk about oxidation numbers and so on. Okay, so we've got 3 reactions, probably two marks for each there. Okay, so first one, aqueous copper sulfate reacts with excess aqueous ammonia in a ligand substitution reaction. You get a deep blue solution formed containing an octahedral complex, which is a trans isomer. Okay, so what we're going to get is we're going to get copper in water is octahedral complex, and that's a light turquoise blue, and we're going to add excess ammonia. And if you remember, you replace not all 6 but just 4 of those water ligands and to produce this. This is a straightforward knowledge recall question really. H2O2 NH3 4 and that's a 2 plus ion, and we should it says it's a trans isomer here. We should mention that this is of course dark blue. You've got to know that. So the reason why it's a transisomer is because you've got octahedral. So you have, there's 4 ligands in the same plane, and then there's one sticking up, one sticking down. Now the water molecules are opposite each other. That is why it's a transisomer, and the ammonias are here. Okay, so if you had the water molecules, which doesn't happen, but if one of these was the water molecule, that would be the cis isomer. These H2O ligands are opposite each other. Right, reaction 2 then. Oh, by the way, there's no redox occurring in that, so we don't need to talk about oxidation number. Reaction 2, copper 1 oxide, all right, which has got the formula Cu2O. It's going to react with dilute sulfuric acid in a disproportionation reaction. A blue solution forms, which is the copper 2+ ion, and the brown solid, which is copper. Okay, again, it's a straightforward recall question, really, and it's disproportionation. Right, let's see why it's disproportionation. Right, we're going to form Cu2+ and Cu. Right, the oxidation number of copper here is +1. Here it's +2, so that one's been oxidized, and here it is 0, so that one's been reduced. Now, it's you're going to get a 1-to-1 ratio of these things, because this one is losing an electron, and this one has gained 1 electron. So it's, it's 1 electron. That's you working out there, right? It's going to be you're going to react that with sulfuric acid. I think I'll put H+ ions in there. So and what happens is you form water. So to balance that, I'm going to need 2H+. Now, if you want the full equation, doesn't it? I think you'll be absolutely fine writing that. You can just put in the spectator as the sulfate, so it'd be Cu2O plus H2SO4. That's going to give you copper 2 sulfate, copper, and water. Okay, now I will take this one here. Reaction 3. Okay. Okay, so we have got here, this is going to be a calculation. Right, copper 2 oxide reacts with nitric acid in a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off, and the solution is left overnight, okay, and it crystallizes. Okay, so what's going to happen there is the equation is going to be, this is a straightforward acid-base reaction, no redox, HNO3. We're going to form copper nitrate, and of course that's going to have that formula because the nitrate's got a 1- copper 2+, and we're going to get H2O, so we need to balance that by doing that. That's the equation there. This is a blue solution, of course, and you're going to get, so you crystallize out that solid. Now if you look at the composition of it, it's got hydrogen in there, so that means it's going to be a hydrated salt of some form. So it's going to be of the formula CuO X H2O, and we need to find out what the value of that X is to finish the question. Okay, so it's we're going to work out the empirical formula of the compound. So we have got here, we've got copper. So let's say in 100 grams, so you're going to have 26.29 of copper grams, 2.48 grams of hydrogen, 11.59 grams of nitrogen, and 59.63 grams of water. So this is the mass, but we need to work out a ratio of moles, so we're going to divide by the AR, the relative atomic mass. So 26.29 over 63.5 for the copper, divided by 1 for the hydrogen, 11.59 over 14 for the nitrogen. The AR of oxygen is 16, divide that by 16. So we work those out, we get right, let's work all of those out. That is equal to 0.414 moles of copper, 2.48 moles of hydrogen, 0.828 of nitrogen, and 3.78 of oxygen. So to simplify the ratio, we're going to divide by the smallest number in the ratio, which is 414. And that is going to give us, to do that, you get 1, that's 6, that's 2, and that is 9. Okay, right, so we've got to find out how many waters we've got in the water crystallization there. Right, so we've got copper nitrate. So that's 1 copper. Now we've got our 2 nitrogens, that's accounting for. We've only got 6 waters in there though, 6 oxygens, sorry. You look, 2 times 3, you've got 6 oxygens. So that means we have got 3 oxygens left over because we had 9 oxygens. So that means it's got to be, the value of X has got to be 3. It's going to be 3H2O. Let's check we've got the right number of hydrogens there. We have, yeah, we've got 6. So that is the formula. Copper nitrate dot 3H2O, and that's the end of that paper.